Hello everyone, and thanks for joining this webinar. My name is Steve Liu, an application engineer at SpeedGoat. Joining me today is Graham Dudgeon from MathWorks.
Hello everyone, this is Graham Dudgeon. I'm Principal Product Manager for Electrical Technology at MathWorks. A great pleasure being with you today.
In today's webinar, first, I will briefly talk about how hardware-in-the-loop testing and digital twins could help marine power system development. Then we will jump into several demos. Graham will go through the modeling part, and I will show you several ways to set up and perform real-time testing with the SpeedGoat hardware. Then I will give you a high-level overview of hardware-in-the-loop solutions from SpeedGoat and MathWorks. Let's start with frequent application use cases for marine industry, and then I will share some real stories from our customers. And then I will zoom in on specific challenges for marine power system and how Hue solution can help addressing these. The SpeedGoat and the MathWorks real-time solution is currently being employed in a manifold of marine applications. For instance, we see teams using a SpeedGoat hardware as test and measurement units for predictive maintenance and diagnosis of marine propulsion systems, but also a flexible solution to rapidly develop and test engine control units and innovative controls for more electrical and autonomous vessels. With shipboard electrical system becoming more sophisticated, we see digital twin and Hue simulation growing as an effective means of speeding up development and de-risk validation of power and energy management systems. We see teams extending the digital twin infrastructure across all development stages. For instance, to help validating specifications and control designs in early development stages, to facilitate training of shipboard crews, for instance, to react properly to emergencies and fault scenarios, and using these detailed shipboard replicas as a tool that helps extending operational life of key shipboard assets and supports with retrofitting and upgrading fleets. Let's see some specific custom success stories outlining some of these use cases. The first success story is Leonardo DRS, building large-scale marine power electronics system for large propulsion motor. Leonardo DRS used the power electronics Hue to design and test power electronics controller. For this, the propulsion motor and the power converter were modeled and simulated on a real-time target machine. Because switching effects of the power converter are important for control strategies, the planned model required time steps in the order of microseconds or less. For this, the planned model had to be executed on an FPGA. With Simulink, Simscape, and HDL coder, Leonardo DRS could develop planned models and deploy them directly to an FPGA for Hue tests. With Hue, the power electronics controllers can be tested against physics-based planned models, including edge case scenarios without worrying about blowing up equipment. Moreover, this Hue simulator was used as a digital twin of the final system that is used to recreate and troubleshoot issues reported in the field. Another example comes from Siemens, who used Hue to implement a real-time digital twin of a gas turbine. The digital twin is implemented on a SpeedGoat real-time machine communicating with the PLC platform via Profibus communication protocol. The digital twin has been deployed on the operational site, and it collects field data that helps run live diagnostics and optimizing performance of the gas turbine asset. The next example is from Naval Sea System Command. In a paper published in Intelligent Shipboard Symposium, the team described a use of a digital twin Hue system that used MATLAB Simulink Simscape as the modeling tool and SpeedGoat as their real-time hardware, which covered all bases of real-time system-level I/O with physical machinery dynamics and power system simulation. The simulated power system is composed of 4 synchronous generators, 4 LC filters, roughly 30 breakers, 20 loads of various types, 2 electrical propulsion drives, and 2 shore power sources. At the same time, isothermal domain modeling is used to model the fuel system, and thermal fluid modeling is used to simulate heat transfer, such as a generator cooling system. The simulation was distributed across 62 speedgoat systems, acting as node simulators. The setup implements over 30,000 separate I/O signals covering more than 8 industrial protocols like Profinet, Ethernet IP, Modbus, UDP IP. Model-based design in Simulink helped to manage the complexity of this system. A major advantage of working in Simulink is that every component is designed and verified in desktop simulation before deploying in the real-time application. Moreover, working with model references allows several teams to integrate and work on the same designs. Note that in our demo section, we will show you how to simulate a similar architecture of a shipboard power system on speedgoat real-time equipment. We can analyze trends in marine power systems and see what it means in terms of requirements for your hull platforms. As marine power systems, we consider an onboard microgrid architectures that are typically composed of generators, energy storage systems, propulsion, and a multitude of loads. Some trends in marine power systems are an increasing demand for high-quality power to support a variety of loads with sometimes challenging power requirements. A transition from AC to MV-DC distribution architectures, and a transition from integrated power systems to integrated power and energy systems. Integrating new electrical components such as flywheel, batteries, capacitor technologies, fuel cells. Advanced electrical propulsion systems, and the integration of advanced controls using communication protocols, for example, to handle energy storage. This means that your hull solution for marine power systems should be able to simulate a multitude of power electronics and electrical drive components, deliver multi-domain and multi-rate modeling and simulation, and high-speed simulation. And at the same time, your solution must support several industrial protocols and I/Os in a flexible, scalable way with commercial off-the-shelf solutions. And your hull platform should have power hull capabilities to test integration of electrical components. To manage the increasing system complexity, the trend goes towards the digital engineering using more digital twins and less hardware. This requires the creation of a land-based hardware facility using a hull and a power hull to de-risk technologies and support the entire life cycle of the system, as shown in that diagram from NAVC. The test system must be adaptable because the marine power system evolves a lot until the ship gets retired. Therefore, the hull platform must support interoperability, for example, with external equipment or several real-time platforms. It must be flexible and scalable. And it must support agile engineering systems such as test automation, collaboration, and continuous integration. Now, in the second part of this webinar, we will use a shipboard power system model to give you several demos. Graham from MathWorks will cover the modeling part, and I will show you several ways to perform real-time simulation with the speedgoat hardware, especially scaling up your simulation with a multi-core and a multi-target setup. Let me hand over to Graham.
In this section, I'll describe MathWorks' value within the context of marine power system technology development, with a particular emphasis on technology readiness. I'll then describe the shipboard power system and give some insights on the modeling decisions I made to arrive at a system-level simulation that was fit for purpose in terms of preparing the model for real-time simulation and satisfying myself that the simulation response was doing exactly what I had prepared it to do. If you give me only one sentence to succinctly state MathWorks' value, then this is it. Model-based design supports all stages of technology readiness, from early stage research through to in-service operation. The Technology Readiness Level Scale, or TRL scale, was originally developed by NASA and quantifies the maturity of a given technology at a given stage of development. TRL1 is your eureka moment, where you have the initial idea and begin conducting basic research. And TRL9 is where you have proven in-service technology. The TRL scale consistently follows key development attributes that you can see on the left. If we first think in terms of model fidelity for desktop simulation, then we typically see different levels of model fidelity coming in at different technology readiness levels. As you begin basic research, you'll have models that are low fidelity. For example, you may have models that have basic functionality in that they convey some high-level system information, such as power flows and component sizing, but which are technology agnostic, meaning the models don't capture specific technology characteristics. As your technology matures, then simulation models that capture more specific technology attributes will be created. For example, you may incorporate models of actual technology types, such as permanent magnet synchronous motors, with field-oriented control. But at the medium fidelity stage, you may still not have vendor-specific information on physical components and control components. A high-fidelity simulation model would have vendor-specific architectures, including parameterization of physical components and control system architectures. The model could also include detailed power electronics, thermal and cooling systems, and communication protocols. Notice that all fidelity levels can track up to TRL9. The reason for this is as your technology matures, you can develop models with different levels of detail that not only supports implementation of your technology, but can also be used for other reasons, such as a digital twin for monitoring in-service operation. Different applications require different levels of model detail. Another view we can take is to explore desktop simulation, real-time testing, and production implementation as a function of technology readiness level. When we look at this view, initial de-risking and feasibility assessment is explored on the desktop before moving to a real-time testing environment where hardware in the loop and rapid control prototyping is conducted to further de-risk control algorithms and physical architectures. The production stage is where algorithms are deployed on actual production hardware, and this is where automatic code generation, which deploys straight to target, offers significant benefits in verification and validation of your algorithms as you near full system deployment. In this section, we'll discuss the two-zone medium voltage DC shipboard power system, and we'll emphasize ideal AC-DC rectifiers, which I'll explain in more detail as we go through this. First of all, an acknowledgement. The models described in this presentation are based on information provided by the Electric Ship Research and Development Consortium. You can go to the following link for more information. Now, I'll make a caveat. So while the system architecture and physical parameters have been honored as closely as possible, there are some differences in the implementation of certain components and control algorithms, and so you won't see an exact one-on-one match. But simulation results that I'll show you in this presentation should be regarded as being representative. You may want to test this model for yourself. I've put this model on MathWorks File Exchange. Let me just show you how to get to this. I'm just bringing over a web browser, and if you type in File Exchange MATLAB, that will take you to MATLAB Central File Exchange. And once you're in File Exchange, type shipboard power system. It's this entry here, shipboard power system in Simscape. And once you're in here, click download. And you'll see you get the zip file github_repo.zip. Okay, so I now have this GitHub repo in my downloads folder. Let me now just bring MATLAB across. So just click and drag it across to the directory that we'll be using. And in the directory in MATLAB, double click to extract it. We see there's a number of directories, but there's this PRJ file, 2zone mvdc.prj. Double click on that to open up the MATLAB project, and you'll see there's a number of project shortcuts. Now, before I get to the models, just a couple of points. There is a PDF here that gives some high-level information on this, but see the tutorial directory, go under there, double-click on Supporting Marine Electrification Technology Development Tutorial, and you'll get more insights into the modeling techniques and modeling considerations that I used as I put this model together. All right, so the models we're interested in are the R2022B models. So I'd just like to open these up and run some simulations and make some observations about these. So let's start with PSolver R2022B. PSolver means partitioning solver, which is one of the solver options within Simscape, which enables rapid simulations. So here we have the model. So let's just quickly navigate this. Full screen, spacebar to go to full screen. We've got two zones. We've got power generation in zone 1, power generation in zone 2. We've got some static loads, 4 switchboards. I've color-coded the breakers here. Red is when they are closed, green is when they are open. And I've also put in a propulsion motor, which in this case I modeled as a permanent magnet synchronous motor with field-oriented control. And we have average value inverters. So let me just talk about that first. So if I double-click on average value inverter, what we do is we feed a modulation wave in to control the inverter, but we're not modeling power electronic switching, because in this case, we're interested in system level response. We're not interested in harmonics for this study. So by using the average value converter, we do not model the power electronic switching. This means we can have a larger time step and more rapid simulation. Let me just go under one of the power generation units. So under gas turbine, you can see here, it's modeled as a synchronous machine salient pole. Got simple gas turbine and governor modeled, and also an automatic voltage regulator and exciter. If you download these models, you can look at this in more depth. This construct here, let me explain this. The purpose of this, I'm not going to focus on the detail, I'm going to focus on the purpose. Its purpose is to provide an ideal conversion between AC and DC, and also to introduce DC voltage droop so I can control the power sharing of the generators. So let me just run this simulation, and while it's running, I'll bring the slides back up. This actually won't take long to run. So here's the scenario that I've set up with this system model. It's very stylized, but it represents a full ahead crash stop. And as you can see, it's piecewise linear, so it is rather contrived. But what it does have quadrant 2 regeneration, as you can see here. Now, I've also compressed the timescale, so I'm doing this maneuver over just a period of 30 seconds, which of course is rather ridiculous, but it does show us the track of the maneuver through quadrants 1, 2, and 3. And what's shown here on the slide is that regeneration period where we're putting energy back onto the system during the quadrant 2 traversal. Let me just get back to the simulation model, so we'll look at some of those results rather than looking at slides. So I'm going to click on Data Inspector. So here's the simulation Data Inspector. I'll just click on PDC_motor. So this is the power. So you can see we go up to just shy of 45 megawatts at full power. And here we are tracking back through, going through that quadrant 2 regeneration. Other things we can look at in the simulation, we could look at duty cycle on the field-oriented control. Let me just zoom in. Space vector modulation has got that classic double hump, so we're seeing what we expect to see. We can also say take a look at the speed reference and the speed measurement. And so we can see here we're tracking up to 50% of rated speed, and then we are reversing speed. So we're seeing what we expect to see. Let's open up the thermal model. I just want to make a couple of observations about this. So first of all, what do I mean by thermal? Well, what I've done is I've added a thermal modeling component to this system, specifically under the propulsion motor. So you can see here on the permanent magnet synchronous motor, I have exposed thermal ports on the rotor and on the stator. And I've modeled, I might add a rather crude thermal system where I've got some conduction and convection set up, and I've got a simple cooling system, simple thermal liquid pipe network. And the pump control simply, if I just go in here, I have a relay, which is saying temperature goes above 329 Celsius, turn the pump on, and then if it goes below 320, then turn the pump off. So a simple bang bang type control here. And I'm just going to simulate this. And while it's simulating, I'll make some more observations about this model. Okay, there it goes. It's simulating now. But let me go back in. There's one more modeling architecture point I want to make here. I have defined two sample times. I have an electrical sample time, which is set as 25 microseconds. And I have a thermal sample time set as 0.01 seconds. Now, the reason for this is thermal time constants are much longer than electrical time constants. And so if I was to model this thermal system at 25 microseconds, I am vastly oversampling that thermal system. I'm also compromising efficient simulation because the thermal equations are more complex usually than the electrical equations. And if I'm sampling at 25 microseconds, it's taking a lot of computational effort. So I'm able to define two sample times. So the system's still connected though. They are exchanging information, but I've been able to split those sample times. And the way I've done it, see these subsystems here, let me just double click on one. So on one side, I've got a heat flow rate sensor and a controlled temperature source. And the other side, I have a controlled heat flow rate source and temperature sensor. So I'm exchanging heat flow rate information and temperature information across Simulink. And what I've got here are rate transitions, which are taking care of the different sample times. And you can see I've got the sample times annotated here, D1 and D2. So in this way, I'm able to use a much larger time step on the thermal side, but still maintain information. And let's just take a look at the simulation data inspector. So we're seeing very similar response. This is the speed measurement and the speed reference. If I just deselect these and now go to the motor, I now have access to temperatures. And you can see here, I've not tuned this very well. This is a very contrived simulation. I've compressed that timescale to 30 seconds. So everything's happening much quicker than it would in real life. And I've done that so we could see some responses. But you're seeing here the effect of this bang bang control on the system. So that concludes my quick overview of the system. Please download the file exchange entry for more detail. And as I said, it includes a tutorial document that steps through the modeling considerations in more detail. Thank you.
Thanks, Graham. Now I'm going to show you how to perform real-time testing. To convert your model to real-time is actually quite simple. You can simply click the Simulink real-time button in Simulink app. Now the model is converted to real-time and you can connect to your target. Click this Run on Target button to build the model, download it to the target, and run the model in real-time. Now the model is running. We have used the Simulink dashboard components to instrument our testing. You can use this control knob here to change the power motor module speed command, and you see the motor speed followed. You can also control the power balance for zone 1 and zone 2. Right now, you see the power generation on module 2 is twice of module 1. That's because the module 2 has only half of the voltage droop of the module 1. So if I make both voltage droop at the same level, like 5%, you see that the power are equal on both sides. But in any case, you see that the DC voltage maintained at the 12 kilovolt level which is good. You can also come to this FOC page to tune your PID. For example, if I put the I term to 0, you can see that you can't get rid of this offset. So I tune the I term up. So now there is no offset. But it's still a little bit slow in the step response. So I'm going to increase the P term, and then you should expect a fast response and no offset. So now the PID tuning is pretty good. You can also go to a Simulink Real-Time Explore window to monitor the task execution time, or TET. This model is running at multi-rates. If you remember, Graham mentioned that this model is running with 2 different domains, thermal running at 1 kHz and electrical running at 40 kHz or 25 microsecond sampling time. So the model is running concurrently in multi-cores, and with that, it allows you to distribute the computation burden to different cores. Here you can see that all the tasks are running within their CPU budget. I want to point out that concurrent execution with multi-rate models is supported natively by Simulink Coder and requires no additional effort from the user. A couple of takeaways from this demo here. First, setting up your real-time testing is quite simple. From converting your model to real-time to code generation and the build process. Also, as you have seen, when you run your real-time simulation in your target machine, you can still stay in your MATLAB and Simulink environment, which many of you are familiar with, when you run your desktop simulation. So you can directly use your MATLAB Simulink resources for running interactive and automated experiments. Another takeaway from this demo is with the right modeling approach, you can let your model run quite fast. For example, use the right solver for your needs. Use multi-rate in the model, and when you use a multi-rate model, not only you avoided unnecessary fast sampling time for slow subsystem, but also it automatically lets you let the model run in multi-core for concurrent execution. You may ask, what if my model is single rate, or if I would like to control how partitions are created and how the computational load is shared across various cores, or how can I distribute simulation across multiple targets for very large models? So in the second part of the demo, I will introduce you to 2 new concepts. First, we will look into a concurrent execution using an explicit partition. As the name suggests, this approach gives you more flexibility in the way you create partitions and balance computational load across various cores. Afterwards, we will talk about distributed simulation across multiple speed-code targets using a high-speed shared memory interface. For the first part, we'll be using the marine power system Hue example shipping within the Simscape electrical product, which basically outlines how to partition a shipboard power system model using a network coupler like capacitor. The model is very similar to what we used in our previous demo, but it's organized differently, so structure-wise it will be easier for partitioning. And also I want to point out that you can choose a different Simscape local solver for your needs. In the previous example, we choose a robust partitioning solver for fast simulation performance. In this example, let's choose a backward Euler solver. It would be slower, but it's more robust and may give you more simulation accuracy. So far, the model is not decoupled yet, and it will be running in multi-rate because we have faster rate for electrical part and a slower rate for mechanical part like turbine. Let's quickly build and run the baseline model on our speed gold machine and check the execution performance. You can see that the mechanical task took a little resource, but the electrical task took most of the computation. In this case, it's about like 80% of the task budget. Now let's decouple the model so we can run the explicit multi-core simulation. Regarding how to do the model partitioning, Simscape Electrical Product provides you many decoupler blocks for both AC and DC networks. Our shipboard example is modeled as a DC network, so we will be using a network coupler like a capacitor. In case you want to learn more about AC network decoupling, you may want to refer to our microgrid hardware-in-the-loop testing webinar. After replaced these measurement blocks with capacitors, we decoupled the left side and the right side. Since the Simscape network is decoupled, we need to introduce a new solver. Next, we unmask the Simscape network coupler blocks and move them up to the model top level. This makes the Simulink connections visible at the top level along with the rate transition blocks, making it easier to group the blocks and subsystems together by sampling time. Then we rearrange the blocks and proceed with the partitioning of the model into 4 parts using reference models. The 4 partitions include the controllers, Zone 1 and Zone 2 power components, and the mechanical parts, which is a turbine. They are all in referenced model, as we mentioned. Of course, you may choose other ways to partition the model. Now the model is partitioned. Let me show you the implementation for explicit multi-core execution. First, in model configuration, you check this box to enable explicit partitioning. You define the tasks with the rates you want. Then in each subsystem, you can assign a unique task to it. When you're done, you can see the task icons in the Simulink model. Because we assigned tasks to a subsystem explicitly, even some rates are the same, you can still control them manually to run on different cores. So this gives you more flexibility when compared to an implicit partitioned approach shown in my previous example. Now you're ready to go with the multi-core simulation. You can see that it's running in a multi-core. You see the mechanical tasks and the electrical tasks. When we run our base model, all the electrical blocks, they ran in 1 task and 1 core. Now it's running in different cores, which distributed the computation load and reduced the risk of overloading 1 single core. So that was the explicit multi-core implementation. Let me show you how to implement the model for multi-target simulation. From this diagram, you can see that I'm using 2 speed-gold performance target machines to run the simulation. I split the model into 2 parts. One is the Zone 1 plus the turbine part. The other is Zone 2 plus the controller part. Comparing with a single target, potentially each target machine could have lower computation burden. Also, since I'm using the reference model, and I could do explicit partitioning and let the model run concurrently in each target, so the computation load could be further reduced, which means it could potentially give you more room to run bigger model. As I mentioned, I'm going to use the shared memory to sync the simulation between the 2 target machines. From hardware level, I'm going to use a SpeedGoat shared memory I/O module, IO907, one on each target machine. From software level, what I need to do is setting up IO907 on each side. One of them will be as a slave and using interrupt trigger to sync with the master, which is on the other target. Each one will need the setup block. You will also need to read and write block and the unpacking block. I also have a short M script to define those setup. I also put an initial condition block here to set up the initial conditions. Right initial conditions help to ensure a stable simulation initialization. Now let's run the model. Let's run the slave side on the target machine 1 and the master side on the target machine 2. We need to run the slave side first. Now slave side is ready and waiting for the master side to trigger the simulation. Now they both started, and let's take a look at the execution performance. As you can see that both targets, they run with a multi-core mechanical part and a controller part, which has different rates. They still took little computation resources. Majority computation is still on the electrical side. However, although the electrical tasks have the same sampling rate, they are still running in different cores. That's because we used explicit partitioning. And you can see that the computation burden was evened out and reduced comparing with the single target multi-core. Let's now look a bit closer into the joint SpeedGoat and the MathWorks Hill solution, starting with the hardware enabler. Benefit from a wide range of real-time target computers that can operate as Hill simulators. The mainstay of Hill testing is the performance machine. It's the most scalable and performant system. It's suited for desktop use, but also suited for rack mounting. The mobile, baseline, and the unit machines are smaller and ruggedized, making a better fit in Hill applications that require more portability and less I/O channels. SpeedGoat target computers come with multi-core processors supporting concurrent execution and co-simulation with FPGAs. They run a QNX-based real-time operating system that supports certification with high integrity safety standards. There is also extensive onboard connectivity, including a varied set of Ethernet-based protocols, serial and video interfaces. The PCI Express architecture serves as the backbone for I/O connectivity with lowest latencies and support for direct memory access and FPGA-based I/O. You can also update and scale your system at any time with I/O expansion units or by implementing distributed simulation architectures, as we have mentioned. Hardware connectivity shouldn't be a hurdle for you. SpeedGoat is supporting key protocols across all major industries. As shown in the previous customer success examples, field buses and network protocols such as UDP, EtherCAT, or Modbus are very common within a marine power system simulation, as well as high-speed protocols and interface such as SPI, I2C, or PWM generation and capture. We also saw the importance of protocols and interfaces enabling distributed architectures and high-scale simulation, such as the shared memory I/O modules used in our demo, but also others like DDS, PTP, or iRig. Overall, more than 200 I/O modules are available and ensure that your workflow remains uninterrupted. Many of our I/O solutions can support you with emulation of various plant components such as battery cells using battery cell emulation units. You can stack several of these modules to build a huge simulator of full battery energy storage systems and complement it with failure simulation and temperature cell units. So you can simulate battery packs down to the cell level and employ that, for example, to test your battery controllers. As outlined with the Navy success story, we can also support you with virtual commissioning of large-scale electric ship plants. For instance, using the Industrial Ethernet multi-node simulator I/O module, which lets you virtualize up to 32 Ethernet nodes like Profinet slave devices. With the help of our project management and production teams, we can provide you with fully customized rack systems, including rack-mounted Hue simulators and easy access to all signals via breakout and I/O panels. We will integrate power supplies, actuators, inverters, and any kind of power electronics, as well as project-specific PCBs for signal routing and conditioning. Maybe you are planning to test electrical equipment via high-voltage interface like a power amplifier. SpeedGoat can support you in building power Hue systems, including selection of suitable power amplifiers according to your voltage, power, and bandwidth needs. We will also provide you with turnkey solutions together with our partners. We have shown you how simple it is to deploy Hue applications, connect to hardware, and experiment from MATLAB and Simulink. But with our unified solution, you benefit from an incomparable integration, not only with MATLAB and Simulink. So let's continue this journey and review some of the key software enablers for your Hue testing. Starting with the SimScape, which can help you with a creation and a deployment of high-fidelity and multi-domain chipboard digital twins. SimScape offers optimized solvers for real-time simulation and is therefore suited for Hue testing. And it provides you with many pre-assembled reference examples that help you to get you started. For power systems and power electronics simulation, you can use specialized products like SimScape Electrical, SimScape Battery, motor control block sets, among others. We have seen these products being successfully employed by many of our marine customers, as shown earlier. These are also teams with whom we maintain a very close collaboration. For instance, SimScape Electrical currently ships more than 60 examples that are compatible and fully tested with SpeedGoat hardware. We also see teams increasingly adopting data-driven techniques to design digital twins. For example, training and using surrogate models that represent high fidelity and nonlinear components, for instance, using reinforcement learning and deploy them as real-time agents to run on SpeedGoat machines. My last pick goes to test automation, which is going to be an important pillar of your Hue testing. You can use MATLAB scripts to automate and expedite testing. You can also interface your Hue system from external programming environments such as Python, shown here. So if your team is using a different programming language, you can spend more time in automating your testing and less time recording in MATLAB. Automating tests using scripting can be of great help, but in many situations you will need tools that support you with the creation and management of test cases, trace tests to requirements, and automated execution of test campaigns. Simulink Test is a great building block within the MathWorks ecosystem that can help you this. Another trend that we see in the field is teams combining the strength of model-based design with agile software development approaches like continuous integration and transferring these techniques to the Hue testing domain. To learn more about the test automation capabilities, I invite you to watch the webinar linked in this QR code. To summarize, for modeling, MATLAB Simulink Simscape is the right tool for shipboard power systems. It allows you to build a complicated model and covers multiple physics domains. From our demos, you have seen that SpeedGoat and MathWorks provide you powerful hardware-in-a-loop solutions with techniques like multi-rate, multi-core, multi-target, and different solvers. It provides you more options to handle large and complicated marine power systems. And also from our demos, you can see that you run your real-time testing from Simulink environment. And both SpeedGoat hardware and MathWorks software are seamlessly integrated. Together, we provide you unified hardware-in-a-loop solutions. That brings us to the end of this webinar, and thanks for staying with us. For more information, just visit our website, speedgoat.com.
You want to learn more about real-time controls testing? Then find additional content linked here.